sklearn, impute, iterative imputer. Description. Iterative imputer is a sophisticated imputation technique in scikit-learn used to handle missing values in datasets. It works by iteratively predicting the missing values in each feature based on the other features in the dataset. This approach is particularly beneficial when dealing with complex relationships between features, where simple methods like mean or median imputation might not be sufficient. Inputs. X the input dataset with missing values. This should be a 2D array-like structure. Estimator the estimator used to predict missing values. This can be any estimator that supports the fit and predict methods. Common choices include decision tree regressor, Bayesian ridge, linear regression. Missing values, the value that represents missing values in the input dataset. By default, this is set to none, not a number. Sample posterior. This parameter controls how the imputer handles the uncertainty in pay predictions. If set to true, it will sample from the posterior distribution of the estimator to generate imputed values. This introduces more randomness into the imputation process and can be helpful in capturing pay uncertainty associated with the missing values. If set to false, it will use the predicted mean from the estimator as the imputed value. Outputs. Imputed, a transformed version of the input dataset where the missing values have been replaced with imputed values. Steps. Initialization. The imputer initializes a temporary copy of the input dataset with missing values. Iterative imputation. The imputation process proceeds in a loop, iterating through each feature with missing values. For each feature, the imputer selects all other features without missing values as predictors. The estimator, e.g., decision tree regressor, Bayesian ridge, is fit on the available data. The fitted estimator is used to predict the missing values in the current feature. The predicted values are used to replace the missing values in the temporary dataset. Convergence. The iterative process continues until a specified convergence criterion is met. This criterion could be based on the number of iterations or the change in imputed values between iterations. Metrics. Mean absolute error measures the average absolute difference between the imputed values and the true values if available. Root mean squared error RMSE measures the average squared difference between the imputed values and the true values. Visualization plots. Scatterplots to visually assess the relationship between the imputed values and the original values for each feature. Histograms to examine the distribution of the imputed values for each feature. Fine-tune parameters. Estimator. Different estimators, e.g., decision tree regressor, Bayesian ridge, can be chosen to suit the nature of the data and the relationships between features. Maxiter. The maximum number of iterations the imputer will perform. Random state sets a seed for the random number generator used in the imputer. This ensures reproducible results. Uncertainty methods. Sample posterior true. This method introduces randomness into the imputation process by sampling from the posterior distribution of the estimator. This captures the uncertainty associated with the missing values, resulting in more realistic imputed values. Predicted mean sample posterior false. This method uses the predicted mean from the estimator as the imputed value, providing a deterministic imputation approach. Challenges and fixes. Challenge 1. Overfitting to the training data. Sample use case that resulted in challenge 1 using a highly complex estimator like a deep neural network for imputation when the dataset is relatively small or the relationships between features are nonlinear. Fixes to challenge 1. Regularization. Adding regularization techniques like L1 or L2 penalties to the estimator can help prevent overfitting. Early stopping. Implementing early stopping during the training process can prevent the estimator from learning too much from the training data. Cross-validation. Using cross-validation to evaluate the performance of the imputation model on unseen data can help identify overfitting. Challenge 2. Computational cost. Sample use case that resulted in challenge 2. Imputing a large dataset with many missing values. Using a complex estimator and a large number of iterations. Fixes to challenge 2. Feature selection. Selecting only the most relevant features for imputation can reduce the computational complexity. Reducing iterations. Lowering the number of iterations maxiter can decrease computational time without sacrificing imputation accuracy. Choosing simpler estimators. Using simpler estimators like linear regression or decision trees can reduce the computational burden. Parallel processing if possible. Leveraging parallel processing or distributed computing can accelerate the imputation process. sklearn, impute, knn imputer. Description. The knn imputer class in scikit-learn sklearn is a powerful tool for handling missing values in your dataset using a k-nearest neighbors knn approach. This method finds the k-nearest neighbors to a data point with missing values and uses the values of those neighbors to impute the missing values. Inputs. X. This is your input dataset, represented as a NumPy array or a pandas data frame. It should contain missing values indicated by none, not a number. N neighbors. This integer parameter specifies how many nearest neighbors to consider when imputing. A higher value means more neighbors are included in the imputation process. Outputs. Imputed. The output is your original dataset with missing values filled in using the knn imputation method. Steps. Finding nearest neighbors for each data point with missing values. The knn imputer identifies the k-nearest neighbors based on the similarity of features. Calculating weighted average. The missing value is then imputed by calculating a weighted average of the corresponding features from the k-nearest neighbors. The weights can be based on the distance between the missing data point and its neighbors. Metrics. Mean. Absolute error may the average difference between the imputed values and the true values. Root mean squared error. RMSE measures the average squared difference between the imputed values and the true values. Visualization plots. Scatter plots. You can visualize the imputed data alongside the original data to see how the imputed values fit within the overall distribution. Histograms. Analyze the distribution of the imputed features to understand the impact of the imputation. Fine-tune parameters. N neighbors. Experiment with different values to see how many neighbors lead to the best imputation results. A larger value might smooth out the imputation but could also lead to overfitting. Weights. You can choose how to weight the contributions of the neighbors: uniform or distance-based. Uniform gives equal weight to all neighbors, while distance gives more weight to closer neighbors. Metrics. Specify the distance metric used to find the nearest neighbors, e.g. Euclidean, Manhattan, etc. Uncertainty methods. Confidence intervals. You could calculate confidence intervals around the imputed values to indicate the level of uncertainty associated with the imputation. Ensemble methods use multiple knn imputers with different parameters and combine their predictions to estimate the uncertainty. Challenges and fixes. Challenge 1. High-dimensional data. The KNN imputer might struggle with datasets containing many features. Finding true neighbors becomes challenging in high-dimensional spaces, leading to less accurate imputations. Sample use case: a dataset with 100 features, where many features are irrelevant or have high correlation, causing the KNN algorithm to be less effective. Fixes to challenge 1. Feature selection. Use feature selection techniques to reduce the dimensionality of the dataset. Before imputation, dimensionality reduction. Apply techniques like principal component analysis (PCA) to project data into a lower dimensional space. Challenge 2. Imbalanced data. If the dataset has an imbalance in the distribution of classes, the KNN imputer might favor imputing values based on the majority class, potentially leading to biased results. Sample use case: a dataset with a rare disease, where most data points are from healthy individuals. This imbalance could lead to the KNN imputer imputing values for diseased individuals based on majority healthy individuals. Fixes to challenge 2. Oversampling. Use techniques like smooth synthetic minority oversampling technique to create synthetic data points for the minority class, balancing the distribution. Undersampling. Remove data points from the majority class to reduce its dominance. Weighted KNN. Adjust the weights of neighbors to give more influence to data points from minority class. Explain torch where the return format should be YAML convertible format as below. Torch where sklearn impute simple imputer. Description: simple imputer is a class in scikit-learn that provides basic strategies for imputing missing values in a dataset. It replaces missing values with a designated strategy, allowing for further analysis and model training. Inputs: X. A NumPy array or pandas data frame containing the dataset with missing values. Each row represents an instance, and each column represents a feature. Missing values: this parameter determines the values to be considered as missing. It can be a single value, a list of values, or none. To represent missing values as none, not a number. Outputs: Imputed a NumPy array or pandas data frame containing the transformed dataset where missing values have been replaced based on the chosen strategy. The output data structure will match the input data structure NumPy array or pandas data frame. Steps: Fit. The simple imputer learns the imputation strategy from the data by fitting on the input data X. It calculates the values like mean, median, or most frequent to be used for imputation. Transform. The trained simple imputer is used to replace missing values in the input data X with the learned strategy. This step generates the imputed datasets. Imputed metrics: imputation accuracy. This metric measures the effectiveness of the imputation method. It can be assessed by comparing the imputed values with the original known values. Data distribution preservation: this metric measures how well the imputation method preserves the distribution of the data. It ensures that the imputed data doesn't introduce significant bias in the overall dataset. Distribution. Visualization plots. Missing value heat map: a heat map visualizing the distribution of missing values across features in the original dataset. Feature distribution comparison: comparing the distribution of a feature before and after imputation to assess the impact of the imputation method on the data. Fine-tune parameters. Strategy: the imputation strategy to use. Choices include mean, median, most frequent, constant. Mean replaces missing values with the mean of the feature. Median with the median. Most frequent with the most frequent value. and constant with a specified constant value. Fill value when using the constant strategy. This parameter specifies the constant value to be used for imputation. Copy a Boolean parameter determining whether to impute in place or create a copy of the data. Verbose, an integer parameter controlling the verbosity level during the fitting process. Uncertainty methods. Variance or standard deviation. The variance or standard deviation of the imputed feature can be used as a measure of uncertainty. This reflects the variability in the imputation process. Challenges and fixes. Challenge 1. Missing values in a feature may not follow the same distribution as the observed values. This can lead to biased imputation and negatively affect downstream analysis. Sample use case: imputing missing values in a feature with a skewed distribution using the mean strategy may introduce bias, as the mean is influenced by outliers. Fixes: consider using more robust imputation strategies like median for skewed distributions, or use techniques like k-nearest neighbors (KNN) imputation. Challenge 2. Imputing categorical features using most frequent can introduce bias if the most frequent category is not representative of the missing values. Sample use case: in a dataset with gender as a categorical feature, imputing missing values with male most frequent category may misrepresent the actual distribution of genders. Fixes: use a strategy like constant to replace missing values with a specific category like unknown, reflecting the uncertainty in the missing values. Alternatively, consider using more advanced techniques like Bayesian imputation for categorical data. sklearn. Impute. Missing indicator. Description. The missing indicator class is a transformer that helps identify missing values in a dataset by creating Boolean features indicating the presence or absence of missing values for each feature. It is often used in conjunction with other imputation strategies, such as mean, median, or mode imputation, to provide information about the missing data. Inputs. Features: a list of column names or indices specifying the features for which missing value indicators should be generated. Missing values: the values considered missing. By default, this is np.none, but can be customized to include other values like na, etc. Sparse: whether to return a sparse matrix. If true, the output will be a sparse matrix of type CP, sparse, CSC matrix. Outputs. Missing values indicator: a Boolean array or sparse matrix indicating the presence true or absence false of missing values for each feature. Features: a list of feature names for the output missing value indicator. Steps. Identify missing values in the input dataset based on the specified missing values parameter. Create a Boolean feature for each feature in the input dataset, indicating the presence or absence of missing values. Return the missing value indicator array or sparse matrix, along with the feature names corresponding to the indicator. Metrics. Accuracy: how accurately the indicator identifies missing values. Completeness: the proportion of missing values that are correctly identified. Visualization plots. Heat map: visualizing the missing value indicator as a heat map can provide insights into the distribution of missing values across different features. Fine-tune parameters. Features: selecting the specific features for which you want to generate missing value indicators allows you to focus on relevant features. Missing values: specifying the specific values considered missing ensures that the indicator correctly identifies all missing values. Sparse: setting this parameter to true can improve efficiency and memory usage for datasets with a high proportion of missing values. Uncertainty methods. None missing indicator does not directly address uncertainty in missing value imputation. Challenges and fixes. Challenge 1: handling datasets with complex missing value patterns. Sample use case that resulted in challenge 1: a dataset with multiple missing values in different combinations across features may lead to challenges in correctly identifying all missing values. Fixes to challenge 1: use a custom missing values parameter to include all possible missing value combinations. Challenge 2: interpreting results. Sample use case that resulted in challenge 2: the missing value indicator only identifies the presence of missing values, it does not provide information about the reason for the missing data. Fixes to challenge 2: consider using domain knowledge to understand the reasons behind missing data and use appropriate imputation techniques.